Hey, good morning, everyone. Mr. Tram here. So, as you are aware or reminded by now, that I will be away this week for paternity leave. Here's what your week will look like. Depending on when you're watching this video, today is Tuesday, October the 11th. Miss Thompson will be in for the start of the class to give you a 20 to 25-minute talk, okay? After that, you will be handed out today's worksheet, 2.2 direct variations, which I'm going to go through in this video in a second. Now, for the next 3-4 days, there will be a lesson with a video just like the one you see right now. So for Tuesday, after the talk with Ms. Thompson, we will go through 2.2 direct variations. There will be homework only today because this is an important topic, and of course I knew Ms. Thompson would be in, so we will be missing about 25 minutes of class. So today's homework is, it should be given to you. To be honest with you, I can't remember if I printed it out or not ahead of time. If I didn't, it is in booklet 2, page 23 to 24. And where's booklet 2 again? You can simply click this link. It'll take you right to the homework books, booklet 2, page 23 and 20. Excuse me, 23 and 24. So it is, if I just scroll down, 23 and 24. And it should be titled Graphing Algebraic Equations, Direct Variation. Okay? So if I didn't print it out for you, so if you don't see this copy in front of you, you can just refer to this, the online version. Obviously, don't write everything out. You can just write this on scrap paper, okay? Read through that and answer it on scrap paper, okay? So that would be the homework for today. On Wednesday, there'll be another lesson, 2.3. Thursday, 2.4. Friday, a two-step equation maze, and there will be a video accompanying all those as well, okay? So let's get to it. So 2.2 direct variations, or variations in graphing. Just give me 1 second here. Just gotta plug this thing in. Okay, so let's take a look at this table for a second. Susan can jog at a steady pace of 150 meters per minute for the first hour. Create a table showing the distance Susan jogs in 0 minutes, 1 minute, etc., etc. So in 0 minutes, obviously distance traveled is, well, 0. In 1 minute, we can travel 150 meters, right? So it's 150 meters after 1 minute. After 2 minutes, it's 300 because we're traveling another 150 meters. In 3 minutes, it's 450 because again, we're adding another 150. So by now, I'm sure you're well aware of what the pattern is because for every minute traveled, we're adding another 150 meters, right? And so forth. Let's just add one more. 750. Okay. Identify the independent variable and the dependent variable and then graph this relationship, which we'll do below. So the independent variable, as the name implies, is the variable that does not depend on anything else. So the independent variable is the variable that does not depend on the other, that does not depend on another variable. It is typically the x value, okay? So if I were to look at the two variables we have here, which are time and distance, which one do we think is the independent, time or distance? Well, does time depend on the distance traveled? No. Time works on its own accord. Distance, however, does depend on the time. So the time in this case is our independent variable. It is our x value. Okay. Let's look at the dependent variable then. So the dependent variable in this case will indeed be distance. Okay. So it is the variable that does depend on the value of the independent variable, on the value of the independent variable. So of course we can see here meters traveled is dependent on the time that has passed. Okay? Now the dependent variable is typically our y value. Okay? So let's just graph this relationship real quick. So if I just go down here, there's a graph there, and let's just graph this. So independent is typically our x-axis, so our time, okay? This is our independent variable. So time, we had 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then our dependent variable, which it looks like I used pink. Oh, whoops, I got the colors all mixed up. You know what? I'm going to correct that. So yellow was our independent variable, which was time. So 1, 2, 3, 4, 5, 6. I'm just going to stop at 6. And then my dependent variable, which was meters. So dependent meters was the distance. So we got 150, 0, 150, 300, 450, etc. So starting at 0, I'm just going to go 150, 300. So each box is going to represent 150 on the y-axis, 450, 600, 750, 900. Okay. Now let's plot the points that we have on the table. So we know we have 0, 0, because if time doesn't pass, you don't go anywhere. After 1 minute, oops, I need to be more specific with my time. Am I measuring in minutes, seconds, hours? Let's go back and see. Looks like we're measuring in minutes. So my time is in minutes. And on my y-axis, we're looking at distance in meters. Okay, so let's plot these points. So after 1 minute, it's 150 meters. After 2 minutes, it's 300. After 3 minutes, it's 450. After 4 minutes, it's 600. After 5 minutes, it's 750. And after 6 minutes, it's 900. So looking at those dots, graphs describe the shape of the graph. It is clearly a line. Where does it intersect the vertical axis? Well, you can see here it intersects the vertical axis, vertical meaning up and down, at 0, 0, right? So where does it intersect? At 0, 0. Write an equation to find the distance in meters that Susan jogs in t minutes. Well, t minutes, d distance, or d meters. Okay, so how can I write an equation to represent this? Well, based on what we have above, we know that the distance traveled, which is our dependent variable, is equal to our rate, which was how fast were we traveling? At a pace of 150 meters per minute, right? So we're traveling at 150 meters per minute. Okay, let's see if this makes sense. So if t was 1, which means 1 minute, how far would we have traveled? Well, 1 times 150 is 150. Well, let's see if t was 2. Well, if t was 2, 2 times 150 is 300, and we get a distance of 300. Okay? What if t was 5? If t was 5, well, let's see what happens when t was 5, or when t is 5. So t equals to 150 times 5, and let's see what we get. $750, a distance of 750 or 750 meters after 5 minutes. Does that make sense? After 5 minutes, we travel the distance of 750. Okay, so for D, what was our equation? It was D is equal to 150 times T. Now E, use the equation to determine the distance that Susan can jog in 40 minutes. Well, now that we have the equation, instead of either using this table and continuing all the way to 40, or instead of graphing this and continuing the time all the way to 40, which would be very tedious, we can instead use our given equation. So we know that distance will equal to 150 times time. Distance is 150 times 40 minutes, because that's what the question is asking for. And let's see what we get. 6,000 meters. So Susan can jog 6,000 meters in 40 minutes. Consider the distance Susan jogged in 2 minutes. What happens to the distance when the time is doubled? What happens to the distance when the time is tripled? So for F, 2, and 3, we're going to revisit this when I'm back in class next week, okay? Right now, I just wanted you to see the connection between the table, the graph, and the equation, which leads me nicely into something we call direct variation. Okay? What is direct variation? It's a situation in which two quantities increase or decrease at the same rate. So in other words, y varies directly as x. Or in other words, distance, which is the example we just did, distance varies directly as a result of time, right? So direct variation describes a specific type of linear equation. Linear, and we mentioned this last week, linear, we can see the word line. Okay, linear equations that when graphed looks like a line. And it could be written as an equation like this, y equals mx, where y is my dependent variable. This is my dependent variable, and x is my independent variable. So in my previous example, y was distance and x was time. The y-intercept of this equation is always going to be y equals to 0. As a direct variation always goes through the origin 0, 0. So what this is saying is, when I'm graphing a line and I end up getting a line that crosses through 0, 0, which is the origin, then I know this line is an example of direct variation. Okay? Oh, variation, not direct variable. Yeah. Now, however, if I had something that looked like, whoops. If I had something that looked like this, this is not a direct variation because you can see it does not cross at 0, 0. Okay. I'm going to skip this point right here. The slope can be found by dividing a y value by its x value. I'm going to revisit that later when we talk about slope. Okay? So let's look at the following. Example 1. Circle the equations below that represent a direct relation or variation. So if I were to remind myself, direct variations should be written in this form, where y represents the dependent. Of course, it could be rearranged, but we should be able to rearrange it into this form, y equals mx, where y is the dependent, x is the independent, and m is what we call our slope or rate of change. It is typically a number. Okay, so let's highlight which ones we think is an example of direct variation. This one is. Okay, so this means that as x value increases, the y value is going to be triple whatever the x value is. Okay. Let's take a look at what other ones. How about this one underneath? Is this it? Y equals to x minus 4. This is not an example of direct relation. Okay, for a couple reasons. We're not increasing by the same factor. Okay, we're not increasing by the same amount. Where if we look back here, y varies directly as a result of x. Okay, so we can see that for this graph, if we were to graph this, it will not go through the origin 0, 0. So y equals x minus 4 is not an example of direct variation. What else? This one is. Okay, so whatever x is, y is going to be 3/4 of that. So that is an example of direct variation. And again, if we were to graph this, we would find that it goes through 0, 0. Here's another one. Okay, whatever x is, multiply that by -4, and it gives us our y value. This is another example of direct variation. Okay, so you can see whatever x is, the negative value of that will give us our y value. What else? How about this one? Okay, so our y, we see our y, we see our x, and our m value in this case is just -2 over 3. Now, I could hear some of you asking, but why is, for example, this one not an example of direct variation? Because as x changes, y is going to change at the same rate. You're technically right. So the reason this is not an example of direct variation is because whatever x is, right, you have to multiply that by -3 and then take away 7 from it. So it's not, y does not change directly as a result of x. Whereas if I were to rewrite this as y equals -3x, then yes, this is an example of direct variation because y will change as a direct result of x. Okay, let me just erase this. Okay, let's look at B. Circle the graphs below that represent direct variation. So if we're looking at graphs, we just need to see if it passes through 0, 0. In this case, does it pass through 0, 0? No. Not direct variation. How about the next one? Nope, doesn't cross through 0, 0. Not a direct variation. How about this one? It sure does. So yes, it is direct variation. And it needs to be aligned too. Here's another one. Yes, this is another example of a direct variation. How about this one? It's not even a line, so no, not a line. And this last one, again, not a line, so not an example of direct variation. Okay, so Tyler works part-time at a local bookstore. He earns $10 an hour. Describe the relationship between his pay in dollars and the time and hours he works. So his pay, let's use P, is equal to 10 times however many hours we work. So I'm going to use T for hours worked, okay? So T is the time in hours worked. And P is the pay in dollars. Okay, so is this an example of a direct variation? It is. The hours worked is, hours worked times $10 per hour gives us the pay, okay? An example of this question where it's not direct variation might be Tyler works part-time at a local bookstore but gets commission. On average, Tyler gets, say, $5 of commission per week, okay? So if that's the case, then it'll be $10 per hour plus the commission. So the number of hours worked doesn't directly give us our pay because we still need to add the $5 commission as well. Illustrate the relationship graphically and represent it with an equation. Whoops, I already did the equation. It's up top, P equals 10T. Graphically, I'm not going to do this part. You should be able to. Actually, you know what? No, I'll do it. So we're going to graph it. Use a ruler, which I am not right now. There's got to be a... No. Anyways, you should be using a ruler. So down here, we have to label whatever the independent variable is, which in this case is time. So 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, 6 hours. So time in hours. Okay? And then over here, we have pay in dollars. So let's go 10, 20, 30, 40, 50, 60. Okay, so after 1 hour, we make $10. After 2 hours, we make $20. After 3 hours, we make 30. 4 hours, we make 40. 5 hours, we make 50. And we are done. And now I just got to connect these, and I'm going to use a different color. So you can see that, sure enough, it's going to go through 0, 0. There we go. So here represents this equation, okay? 1 week, Tyler works $9. Find his pay for that week. Well, we know that the pay is equal to 10 times T, so which means the pay would equal to 10 times 9, which would equal to $90. So therefore, Tyler made $90 that week. Now, at the end of March break, Tyler was paid $400. So let me rewrite the equation. So we're being told that the pay is $400 now. So 400 is equal to 10 times T. How many hours did he work? So you will need to use your solving equation skills from last week. Well, if we need to find T, I'm going to divide both sides by 10 to get T on its own. So if I divide 400 by 10, I will get 40. So therefore, Tyler worked 40 hours. Okay. How much would Tyler have to work in a week to get paid $155? E is the exact same question as D, except instead of 400, it's $155. Okay. So for example 3, I want you to try example 3 and 4 on your own. For example 3, state the equation that represents each situation. Y varies directly as x and the slope of variation is 9. I'm going to do this first one for you because it's pretty wordy. Not a big fan of this question, but this question is essentially saying that y will change as a result of x and the variation is 9. We're done. Okay? Now, try B and C on your own and example 4. Once you're done that, hopefully I printed this out ahead of time. I'm really hoping I did. If not, it should be 23 and 24. 23 is just reiterating what I just said, okay? And then 24, for you to pretty much redo the questions that you just did. So write an equation for each of the scenarios, and then you're going to graph 2 of these. So, for example, there are 1,000 meters in 1 kilometer. Write a formula to convert meters into kilometers. Convert meters into kilometers. So if we know that 1 kilometer is equal, I'm going to put 1 kilometer equals to 1,000 meters, right? 1,000 meters. So if I want to know how many kilometers there are, so I'm going to let y represent the number of kilometers, and I'm going to let x represent the number of meters, then our equation is just simply y equals 1,000 times x. Hold on, this is frozen. Give me a sec. Oh, come on. Let's go. Okay, there we go. Okay. All right, so if I scroll down here, so see these 2 graphs down here? You can choose to choose any of these 6 and graph it. Now you know that these are examples of direct variation, which means that your 2 graphs that you sketch should go through 0, 0. If they don't, then you probably made a mistake somewhere, okay? All right. Let me just erase this. Oh wait, I made a mistake here, didn't I? I had these 2 switch. So x should represent the number of kilometers, yeah. So let x represent the number of kilometers. Yeah, that makes more sense. And let y represent the number of meters. There we go, that makes more sense. So if there's 1 kilometer, 1 times 1,000, that gives us 1,000 meters. If it was 2 kilometers, 2 times 1,000 gives me gives me 2,000 meters and so forth. There we go. Okay, and as always, you can always check your solutions at the very bottom of this package. So if you just go all the way down, you can see answer key to page 17, page 18, page 19, page 20, go to page 23 and 24. Okay? Now, part of our observation and conversation talks I had with not all of you, but most of you, was for you to get in the habit of checking your solution to identify mistakes, right? So once you're finished, check your answers here, and then you're done for the day. Okay. All right, so tomorrow there'll be another video for another lesson. In the meantime, have a good night or a good day, and we'll see you virtually tomorrow.